Hey guys, today we are looking at 6.5, which is all about properties of logs. So now that we've established what logs are, how they behave in terms of like how we can convert back and forth between exponentials in them, how we find their inverses, and how we graph them, now we're getting into the different properties of working with non-perfect ones and kind of how they interact with each other as well. So we've got these three different properties that we're going to be dealing with here in box one, and they stem directly from our three main exponent rules that we looked at with our exponent rules back in the first section of this chapter. So remember, in our exponent rules, if we had two bases being multiplied together that had two things being multiplied together had the same base, we added their exponents. If we had two bases being divided, we would subtract their exponents, and then our power rule told us that if we have an exponent being raised to another exponent power, we would multiply those together. Now you can see here our three properties of logs tells us that if we have the log of a product, so we have two things being multiplied within the same log, we can rewrite that as the two separate logs being added together. So our base stays the same, so log base b of m times n is the same thing as log base b of m plus log base b of n. So it's still the same process. Multiplication becomes addition. It's just as two separate logs. Our quotient rule here, log base b of m divided by n, or m over n, is a fraction, which we know is division. I still follow the same expectation. I would take top minus bottom. So the numerator here is m, so log base b of m minus log base b of n. And then last but not least, our power rule tells us that if we have something being raised to an exponent power within that same log, I can just take that exponent in my log and bring it out in front and multiply it. So I'm still doing multiplication when I have power rule. So what we're going to be doing today is basically just working with those three equations, those three different properties, to simplify, rewrite, evaluate, condense, and expand different logs so that they are written in different ways. So over here in box 2 that we're doing, we're given two different pieces of information. So instead of having to evaluate, we're given an approximate value for two different logs. So they're telling us that log base 2 of 3 is approximately 1.585, and log base 2 of 7 is approximately 2.807. So we're going to use those two pieces of information to evaluate the following three logs. So what we have to do is rewrite them. So we're going to use our properties that we just looked at back in box 1 to try and rewrite these so that it's just in terms of log base 2 of 3 and log base 2 of 7, because those we have our approximate values for. So if we can get it into just log base 2 of 3 and log base 2 of 7, we will be able to just substitute those values in there and get our solution. So for number 1, we have log base 2 of 3 divided by 7. So we have a fraction going on there. If we look back at quotient rule in box 1, that tells us that I can rewrite this as log base 2 of 3 minus log base 2 of 7. That's just my quotient rule. Once I've done that, this would be an expansion here. I have my log base 2 of 3 and I have my log base 2 of 7. They tell me what those values are. They tell us that log base 2 of 3 is 1.585 and log base 2 of 7 is 2.807. So I can just do that subtraction. You can use your calculator if you need to. 1.222. That is the approximate value of log base 2 of 3/7. Okay, moving along. For number 2, we are given log base 2 of 21. Well, log base 2 of 21 we don't know the value of. But again, if we're trying to put it in terms of log base 2 of 3 and of 7s, what we're going to have to do first, before we can do any kind of expansion, is recognize or realize that log base 2 of 21 could be also log base 2 of 3 times 7. Because 3 times 7 is 21. Once I have that set up as a multiplication, if we look back at our product rule, in box 1, that means that I can rewrite this as log base 2 of 3 plus log base 2 of 7. Because if I have a multiplication happening inside my log, I can expand that as the sum of those two separate logs. So now that we have that expanded out, we have everything in terms of log base 2 of 3 and log base 2 of 7. So I'm just going to do that substitution again. 1.585 was log base 2 of 3. Log base 2 of 7 was 2.807. So I just add those two together. We get 4.392. 4.392. That's log base 2 of 21. Approximately. Okay. Last but not least, number 3 here in box 2, we've got log base 2 of 49. Log base 2 of 49. So there's two different ways of approaching this problem. And I'll kind of just outline both of them, and then we'll do one of them. So what we have to do, again, is put it in terms of either 3s or 7s. So again, we know what log base 2 of 3 is. We know what log base 2 of 7 is. So it has to be written in terms of one of those two things. So what you have to rewrite this as, you've got two different options. So we could look at this and say, all right, well, 49 we know is 7 squared. So I can do it that way. Or if I wanted to, kind of the same idea, log base 2 of 7 times 7. Either way is totally correct, and it's all in terms of 7s. So log base 2 of 7, we know what that is. So if you're going to go with that second option, if you did log base 2 of 7 times 7, it would look exactly the same as that previous problem. So just for the sake of doing something a little bit different, let's go with that first option. Let's consider log base 2 of 49 as log base 2 of 7 squared. So that would be a power rule for our logarithm. So that's over in box 1, the very last one. Power rule tells me that if I have inside my log, if I have something being raised to an exponent power, I can take that exponent and just bring it out in front. I'm just multiplying by that exponent instead. So instead of having log base 2 of 7 squared, I could have this as 2 times log base 2 of 7. And from here, my 2 stays, but I know what the approximate value of log base 2 of 7 is. They tell me that the approximate value is 2.807. So 2 times 2.807 gives me 5.614. And that is the approximate value of log base 2 of 49. All right, so moving on to box 3. So box 3 is all about what's called expanding and condensing. Now, with expanding and condensing, we're basically doing the same thing we just did with expanding, with that previous set of problems. It's just that here we're working more generically. We're not working with approximate values of anything. It's just trying to take a single log and expand it out as far as we can. So all we're going to be doing is just kind of using whatever rules we can use. So we can use power rule, we can use product rule, we can use quotient rule. Now we have to follow kind of the reverse of order of operations. So we have to look at what's the biggest operation affecting the most number of things and do that first for our expansion. So for number 4, we have our natural log, so ln of 5x to the 7th power over y. So our biggest operation here, the thing that's affecting the most number of terms, is going to be that fraction, that division that's happening there. So that's going to be the first thing I have to expand out. So when I expand this, quotient rule, right, our division, tells us that I have the natural log, which I write my ln's as cursive just to make them a little more distinct from ones. So natural log of 5x to the 7th power minus natural log of y. So I'm just taking that division and splitting that up into two separate terms with subtraction. And we know that subtraction-wise, it's always top minus my bottom. So my numerator was 5x to the 7th. So now that's my first term, and then my denominator was y. From here, My furthest right term is all the way simplified and expanded out as far as we can. Natural log of y cannot be rewritten any further. My first term can, however, my 5x to the 7th power, I have two different operations happening there. So I have 5 times my x to the 7th power. So I have a product there, I have a multiplication happening, and I have an exponent. So looking at my operations, the thing that affects the most number of terms is that multiplication, because my 5 is being multiplied by my x. The exponent of 7 is only affecting the x. That 7 is not affecting the 5. So that's why in this case, I have to go with the thing that affects the most number of our terms. So if I'm going to expand this, that is right now a multiplication, when we expand a multiplication, that becomes an addition. So I end up with ln of 5 plus ln of x to the 7th power, and then I still have that natural log, that ln of y. So ln of 5, that's done. That's as far as I can expand that out. My ln of y, again, that's already been done and expanded as far out as we can. Now all we have to do is that exponent in that middle term. And like we just did on number 3, if we're trying to get rid of my exponent, if I'm trying to get that in the main level, that exponent is just going to become my coefficient out in front. So my final expansion, the thing that's all the way expanded out as far as possible, my natural log of 5 plus 7 times the natural log of x minus the natural log of y. And that is expanded as far as possible. Condensing is just the reverse of that process. So I'm starting with something that's expanded out amongst a multitude of different y values, or a multitude of different logarithms. I'm trying to condense it down into a single log. So here I'm dealing with my common log, right? We don't see a base in my log, so I'm dealing with log base 10. That might be significant sometimes it's not. In this case, I'm just going to work on trying to condense things together. So when I'm condensing, I look at individual terms first. So I try and condense them down within each individual log. So my common log of 9, that's not anything I can do. Here with my middle term, I can bring that 3 back in as an exponent. So log of 9 plus log of 2 cubed minus log of 3. So I can just rewrite that real quick. 2 to the 3rd power is 8. So that's all I'm doing for this process here. And now for addition and subtraction, it's just kind of going from left to right. So just like when we're going order of operations wise, if we get to that multiplication / division step, we're just supposed to work left to right. So we're going to go ahead and do that. So when I combine log base 9 plus log of 9 plus the log of 8, that would become multiplication. So log of 9 times 8, and that's still minus 3, log of 3. So when I condense those down all the way, log of 9 times 8 over 3. So we can see here, instead of multiplying it out, I just decided to leave it expanded in terms of my numbers, because now I can just simplify that. That 9 over 3 reduces to just 3. 3 times 8 is 24. So my final condensing is just the log of 24. Log of 24. And those ones, there's a lot of different things that can happen. There's a lot of different nuances to expanding and condensing. The board game that I was telling you guys about that we're playing next week, our Log Races board game that I made a couple of years ago, it's looking at different skills. Some of them are conversion problems where you're just going back and forth between exponential and logarithmic form. And then you do have a whole kind of set of cards that are expanding problems and a whole set of cards that are condensing problems. So we'll take a look at those and do plenty of practice on those as well. All right. Last but not least, box 4, change of base formula. This is super useful, especially for those of us who don't have a fancy pants calculator. For those of you who don't have a TI 83, 84, or something similar to that, we've been kind of limited in terms of what we can evaluate using our calculator based on what the base is. All of us have the capability of doing a common log, right? That was log base 10, just log of whatever. And we've been capable of doing our natural log, our ln, log base e. But for the most part, that's all we've been able to do. Not many of our calculators have the capability of evaluating a log for a particular base. And this change of base formula allows us to be able to do that. It opens it up for us to be able to evaluate any log that we want to using this change of base formula. And what it's telling us, we have log base b of a. So our base is b. We're trying to evaluate a for that base. If we can't do that on our calculator, what we can do is change the base to something totally different. So you can see here, this first equation, this first equal sign afterwards, I'm now doing log base c of a over log base c of b. So now my base is the thing I'm evaluating in my denominator. My thing that I was originally evaluating, my a, stays in the numerator. Now, we don't usually use this middle one because that's not really useful to us because we don't, I mean, you can pick whatever you want, technically, yes, sure. But what's more useful to us are these last two. We can choose our base to be 10, or we can choose our base to be e for that change of base formula, and that allows us to be able to use our calculator for that. Because again, we have those buttons on our calculator that is just log of 10, that's our common log, and we have our ln, which is our natural log, log base e. We have those shortcuts on our calculator. So if I'm trying to evaluate something here in number 6, if I'm trying to evaluate log base 3 of 8, that's not something we could just do in our head. When we were evaluating these before, what this is asking us is 3 to what exponent power gives me 8, which is not going to be a very nice number because 3 to the second power is 9, so it's a little bit less than 2, but it's not going to be a whole number. But our calculators can't do that for us unless we use this change of base formula. So what I can do if I'm trying to evaluate log base 3 of 8, I could rewrite this as log 8 over log 3. And your calculators are capable of doing this in one calculation. You just have to put parentheses around your log of 8 and then parentheses around your log of 3. When you do this, log of 8 over log of 3, you should get 1.893. 1.893. So again, just a little bit less than 2, which makes sense because 3 to the second power is 9, so a little bit less than that would be 8. It doesn't matter which one you use. Here in that one I used just my common log. You could do the exact same thing with our natural log. It's just whatever is easier for you in your calculator in terms of your buttons. If I'm trying to evaluate log base 6 of 24, I could also just do, all right, well, let's just say natural log of 24 over my natural log of 6. We evaluate each of those on our calculator. We should end up with 1.774 for that final evaluation, which again makes sense because 6 to the second power is 36, 6 to the first power is 6, so somewhere between 1 and 2, 1.774 seems like a pretty realistic number. So again, just make sure you guys try that out if you're struggling with how to type it in on your specific calculator, the one that you use on quizzes and tests. If you use the one that's on your computer, if you use, one in my classroom, if you've got your own and are not sure how to type stuff in, just let me know. We can work through that together. But yeah, that's all we got for today. So your homework is down there at the bottom of the sheet. It's page 331, 4 through 40, every other even. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. We'll see you soon.